Section 3.4 is all about concavity and points of inflection. So when we describe a function, or a part of a function rather, as being concave up, that is where our graph is going to curve upwards from the tangent line. So if you can imagine on this graph, like anywhere that I have a tangent line, so like imagine there, or maybe down here, the graph curves upward away from the tangent line, and the tangent line is always below the graph. So similarly, when a function is concave down, it's going to curve down away from the tangent line, no matter where I draw it. And a function can change concavity, and when that happens, we call that a point of inflection or an inflection point. So if I think about it, a function is concave up where its first derivative is increasing. So again, if you imagine the slope of these tangent lines, this one has a negative slope, right? And as I get closer and closer and closer to the minimum, it still has a negative slope, but the slope is getting less negative. At the minimum, we know the slope would be exactly 0 if I imagine that tangent line. Man, I'm drawing a lot of tangent lines on this. And then as we get away from the minimum, now our slope is positive and it gets steeper and steeper and steeper. So similarly, if a function is concave down, its first derivative is decreasing. So again, I might start off with a tangent line that has a positive slope. It's really steep. It gets less steep. It becomes 0. And then it becomes negative, and then our slope becomes more negative. So if we think about the relationship with that in our second derivative, our big, very important takeaways in this box are that our function f is concave up at any particular value x equals a if f prime is increasing at a, and that would mean our second derivative at a is positive. So similarly, we are concave down at a particular value if our first derivative is decreasing, meaning our second derivative is negative. And then finally, a point of inflection happens anytime we change concavity. So that's either where f prime changes from increasing to decreasing, or vice versa, decreasing to increasing, or where the sign of our second derivative changes. So very similarly to how we determine the location of a relative min or max, we're going to have a really similar process for determining the location of a point of inflection, or where our function is concave up or down. So in this first example, we are asked to determine the intervals on which f is concave up or down and determine the location of the points of inflection. So in order to do this, we need to find the second derivative because we can use our number line sign test on the second derivative. So to do that, I need, well, my first derivative. So f prime of x is just x squared minus 4x minus 5. And then I need to find my second derivative, and that's going to be 2x minus 4. And so similarly, I want to look for where my second derivative equals 0 or where my second derivative is undefined. So this is really similar to how we find critical values. In fact, these are sometimes called hypercritical values. AP doesn't use that language though. They will call these candidates for points of inflection. So I know 2x minus 4 is never undefined, but I want to set my second derivative equal to 0. So if 2x minus 4 is equal to 0, then I know x must equal 2. So 2 is a candidate for a point of inflection. All right, so we said step 1 was to find our second derivative. Step 2 was to set that equal to 0 or find where it's undefined, if I'm kind of thinking of these as steps. So step 3, I'm going to make a number line. So we're not on a closed domain. I'm just going to put my value of 2 in my number line. And I have to be careful here. I am plugging this back in to the second derivative. So I want to test the second derivative. So if I pick any value less than 2, let's say 0, it's kind of my favorite number. If I plug that into my second derivative, I would get f double prime of 0 is 2 times 0 minus 4. You could probably just do this in your head. You don't really have to show your work for this. And I can see that that's going to be negative. So what I know about the concavity of f there is that f is concave down. And then similarly, I always want to test the other side. I don't want to assume that there's a sign change, although we can tell in this one there will be. If I pick, let's say, the number 3 here and plug this into my second derivative, I get 6 minus 4, which is positive. So my function f is concave up. So it's concave up from 2 to infinity. So our final step is to answer the question, or questions in this case. So first we were asked to determine the intervals on which f is concave up or down. We need to answer those, and we need to provide a justification, but the justifications for everything we're going to do is like what's in these two boxes. So we could say that f is concave down from, or I could say on the interval negative infinity to 2, excluding the 2. And our reasoning for that is because our second derivative is negative. Now, it is also true here that our first derivative is decreasing on this interval, but to use the language of science, for example, claim, evidence, and reasoning, our claim is that f is concave down. The evidence that we used was our number line, and the thing we tested was the second derivative. So I want my reasoning to match the evidence that I found, that my second derivative is negative or less than 0. So then f is concave up on the interval from 2 to infinity. And again, the reason for that is where our second derivative is positive. And then to answer the last question, determine the location of points of inflection. We could say f has a point of inflection, or inflection point, either way, at x equals 2 because, well, if I think how I know that, that is where our second derivative changed from negative to positive. So I could say my second derivative of f changes, oops, I started to write the word of, changes from negative to positive. All right, let's look at this next example. We are given a function f equals e to the x times sine of x, and we're given a closed interval, 0 to 2 pi, and we are asked to determine the intervals on which f is both decreasing and concave down. So let's take that one at a time. For f to be decreasing, that's where our first derivative must be negative. For f to be concave down, that's where our second derivative must be negative. So we are looking for the interval or intervals from 0 to 2 pi where both our first and second derivatives are negative. So we need to test both of those. So let's start off with our first derivative. If I find my f prime, I must use the product rule here. So we get e to the x sine of x plus e to the x cosine of x. And I know that if I'm trying to find where this is equal to 0, I probably want to use factored form here. So e to the x times the sine of x plus the cosine of x. All we could do is pull out a GCF. And if I'm setting that equal to 0, again, in factored form, I can use the zero product property. So I need to look for any values of x that would make e to the power of x equal to 0, or would make our other factor, sine of x plus cosine of x, equal to 0. Now, e to the power of x can never be 0. We know that we have an asymptote there. We're not going to reach 0. So I really just need to solve this equation, sine of x plus cosine of x equals 0. And that is going to be where the sine of x is equal to the negative cosine of x, or vice versa. the cosine of x is equal to the negative sine of x. So if we're looking at this closed interval from 0 to 2 pi, I might want to just imagine my unit circle. So I know I've got 0, pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2, aka 2 pi. So I know that, first of all, for sine of x to be negative cosine of x, for those to have the same value, the same absolute value, but have opposite signs, that could only happen in quadrant 2 or in quadrant 4. So if I think about where in quadrant 2 would sine and cosine have the same absolute value, that's going to be, that's always going to happen on our pi over 4 triangles, or our 45, 45, 90. I know I'm talking about degrees when I say that. So that's going to happen first at 3 pi over 4 in quadrant 2, and then at 7 pi over 4 in quadrant 4. So we get that x equals 3 pi over 4 and 7 pi over 4. All right, so those are the values where f prime is equal to 0. Now, I'm going to come back to those in a second. We could reason about those now, but I'm going to go to the second derivative. So we said we need our second derivative to also be negative. So if I take my second derivative, you could either use the product rule in this form, or we could take the derivative in this form. It doesn't really matter. We should get the same thing either way. I'm going to use the product rule. So the derivative of e to the x times sine of x plus cosine of x plus the derivative of sine of x plus cosine of x times e to the x. Well, that's going to be cosine of x minus sine of x times e to the x. So maybe I should have, we could factor out our GCF of e to the x, or we could distribute it. I don't really know which seems easiest. They seem like the same amount of work. I'm going to factor it out. So I'm left with sine of x plus cosine of x plus cosine of x minus sine of x. And my SIN signs have opposite SIGN signs, so I can cancel those out. So I get e to the x times cosine of x plus cosine of x, which is the same as 2e to the x cosine of x. Okay, so now, again, we want to set this equal to 0. So if I set my second derivative, not of 0, sorry, set it equal to 0, that's going to be where 2e to the x cosine of x is 0. And I know 2 is not 0. E to the x can't be 0. Cosine of x, however, can be 0. And again, where would the cosine of x be 0 on this closed interval from 0 to 2 pi? Well, that's going to happen at the top of our unit circle at pi over 2, and at the bottom at 3 pi over 2. So we get pi over 2, and we get 3 pi over 2. All right, so I'm still going to make a number line, but I'm going to be careful here because I'm going to have to put a lot of stuff on this number line. So if I think about my first derivative first, actually, you know what, the first thing I'm going to do is I'm going to put these numbers in order on my number line so I don't put like pi over 2 in the wrong spot. So pi over 2 was our first thing to consider. That was where our second derivative was 0. Then 3 pi over 4. Then 3 pi over 2. Then 7 pi over 4. And you know what? I put arrows on my number line, but really this is a closed number line from 0 to 2 pi, so we can kind of just ignore those arrows. All right, so I know that I'm going to start with just one at a time. So I'm going to start with my first derivative. And I'm really just looking from 0 to 3 pi over 4. I don't need to worry about pi over 2 because that's not a value where my first derivative equals 0. So from 0 to 3 pi over 4, I want to think about the sine of f prime. And again, I'm going to use this factored form of f prime. Now, I know that e to the x is always positive no matter what I plug in for x. So all I need to think about is sine plus cosine. And I could pick any value between 0 and 3 pi over 4 to test that. Well, how about just pi over 4, or just like anything in the first quadrant? Sine plus cosine of x in the first quadrant is going to be positive because I'd be adding two positive numbers. So a positive number times our positive e to the x means that f prime is positive on this interval. So like our first derivative is positive from here to here. So then we want to check our first derivative from 3 pi over 4 to 7 pi over 4. So from 3 pi over 4 to 7 pi over 4 right here, I could pick any value. I could use pi, for example. So if I plug pi into my first derivative, well, e to the power of pi is positive, sine of pi is 0, cosine of pi is -1. So my first derivative, I get e to the power of pi times -1, which is a negative number. And then finally, from 7 pi over 4 to 2 pi, so this part of the unit circle right here, when I test that, I'll notice that I'm going to get a positive derivative again, because again, I know e to the power of x is always positive, and even though sine is negative, cosine is positive. And if I think about my triangles, my like horizontal leg of my triangle is longer than my vertical leg, meaning the absolute value of cosine is greater than the absolute value of sine. So from 7 pi over 4 to 2 pi, we have a positive first derivative again. Okay. So now let's check our second derivative. Now, we said that for the question we're trying to answer, we've really narrowed this down. I mean, we could test our entire second derivative, but we've narrowed this down to an interval where f prime is negative. And that's going to be from 3 pi over 4 to 7 pi over 4. So f is going to be decreasing on this interval where it's increasing on the other intervals so far. So I could really just hone in on this part. So now I want to consider my sign of my second derivative. So I'm not even going to look between 0 and pi over 2. I could, but I know I can rule that out because f prime is positive there. So from pi over 2 to 3 pi over 2, so pi over 2 up here, all the way to 3 pi over 2. Remember, my second derivative is 2e to the x cosine of x, and I know the 2e to the x piece is always positive, so I really just have to think about the sign of cosine, and that is where cosine is negative. So on this interval, my second derivative is negative, although I don't really care what's happening before 3 pi over 4, and then it's negative here until I get to 3 pi over 2. And then on the other side of 3 pi over 2, we should still check. So from 3 pi over 2 all the way till we get to 2 pi, well, my second derivative is going to be positive there because cosine is positive in quadrants 1 and 4. So I have a positive and a positive. And even though we didn't check, our second derivative would have been positive back there as well. So if I look for the places where both f prime and my second derivative are negative, that's really only happening here on this interval from 3 pi over 4 to 3 pi over 2. So that's where our concavity will be concave down. Sorry, I should have done this one in purple. My color scheme is getting messed up here. All right, because we said we'd be concave up here. All right, so to answer our question, we could say that f is decreasing and concave down on the interval from 3 pi over 4 to 3 pi over 2 because f prime is less than 0 and our second derivative is less than 0. Now, it might actually make our answer stronger to assign each reasoning to each fact, to say like f is decreasing where f prime is less than 0 and f is concave down where our second derivative is less than 0. This happens on the interval 3 pi over 4 to 3 pi over 2.